All right, so this is the third lecture on Cohen-Macaulay rings and modules. Let me first recall what we did last time. So we characterized what is called grade IM. Here, I is an ideal, R is a Noetherian ring, M a finite R module. Grade of IM is the maximal length of an M regular sequence in I, and we showed that this length is equal to the infimum. Also, IM is not equal to M. That is part of the definition when we say M regular sequence in I. Okay, IM is not equal to M. It is the infimum of I, so that X I R mod I M is not equal to 0. And we did a more general version of this. We understood if n was another finite module, then these x i's of nm, okay, n is another finite R module, then x I nm is equal to 0 for all I less than the grade of annihilator of n on M, and if this grade is n, then the nth text is not equal to 0. So this vanishing result implies this result. You just take n equal to R mod I. Then we get the characterization of length of maximal M regular sequence contained in an ID through the vanishing and non-vanishing. And this is an important property. I am not equal to M. We also showed that the X modules, okay, these X modules can be all 0. These X modules can be 0 for all I, if and only if the annihilator of n and the annihilator of m, they are co-maximal. Okay, so if this says that if I am equal to m, then the x I r mod I m is 0 for all I. So we cannot use X to detect the grade of an ideal on a module in this case. So that is why we impose this condition, IM is not equal to M. Okay. Now, before we can, I can give the definition of Cohen-Macaulay module, I need to prove one more vanishing theorem. This is called the Ishiba vanishing theorem. Okay, so now M and N are any finitely generated modules over a local ring. Finite R modules where Rm is a local ring, local Newtonian ring. Then the X modules of Nm are 0 for all I less than depth of M minus dimension of N. Okay, so this result, which early result, which characterized the vanishing of X of Nm, that was referring to the grade of annihilator of N with respect to the module. Here we don't have any such thing, but the ring is local ring. Okay? The ring is a local ring, and I have any two finite R modules. Then all these X are 0 below this number, which is depth of M and dimension of N. Remember how did we define depth of M? Depth of M over a local ring is really the grade of maximal ideal with respect to M. So this is the length of maximal M regular sequence contained in the maximal ideal. So that is the depth of M. And of course, you know dimension, and take this difference, depth of this module minus dimension of this module. Below this number, all the X modules are 0. This is a very useful theorem for detecting vanishing of X. Okay, so let us prove this, and that will lead to the definition of Cohen-Macaulay modules. Any doubts so far? Yeah. So let us prove the proof of the vanishing theorem, proof of Ishiba vanishing theorem. So we want to prove that all these X modules are 0 for I less than depth of M minus dimension of N. So suppose the dimension of N is R and depth of M is K. Okay. So we shall apply induction. There are these two numbers floating around here. Of course, dimension of R and depth of R are other two numbers. Usually these things are proved using some induction. And when it is not clear what is the suitable number to apply induction unless you first try. So the induction on dimension of N really works. And you will see in a minute why this works. So we apply induction on dimension of N. So suppose this dimension is R equal to 0. And you know that the dimension of N is dimension of R over annihilator of N. Because dimension of N is dimension of the topological space, which is support of N in Zariski topology. And support of N is the variety of annihilator. Okay. And variety of annihilator contains all primes which contain the annihilator. And this is the set of all primes whose images primes of R which contain annihilator. So take their images in R mod annihilator of M. So these two dimensions are equal. So if R is 0, that means R mod the annihilator of N is Artinian local ring. This is an Artinian local ring. And so therefore, there is only one prime ideal here. Spec of R mod annihilator of N is simply M mod annihilator of N. So let me write annihilator of M to be I. So it is equal to M mod I. That is the spec. Okay. And so that means this means that radical of I is the maximal ideal. Yeah, radical of I is maximal ideal. And so I need to prove, we need to show that x I r n m is 0 for I less than depth of m. Okay, but now annihilator of n is m primary. Yeah. So by the recess theorem, okay, we know that I proved last time that grade of I m is same as grade of radical of IM. And remember, this was basically because of the local characterization of grade. Grade of IM turned out to be the infimum of depth of M localized at P over the local ring Rp, where P is in the variety of I. Okay. So, but variety of I is same as variety of radical of I. So grade of IM is same as grade of radical of IM. And so by recess theorem, now this x I r n m is 0 for all I less than depth of m. Because depth of m is grade of mm, but m is the radical of I, and this is the grade of I. Okay. And I was the annihilator of n. Okay. And we know this characterization through text. So we are done when dimension of n is 0. So when r equal to 0, we have proved Ishiba vanishing theorem. Is this fact clear? Any doubts on this? Yeah, is any step unclear here? Speak up. Yeah,
So
otherwise I
here,
will start asking you questions.
so here, how do we know that we have to apply induction on dimension of n?
Yeah,
Like, is it possible to proceed in this by applying induction on depth of m instead of dimension of m?
it may be possible. So there can be multiple proofs. So here one takes the simpler proof, and right in the first step, you see that when dimension of n was 0, it reduced to a theorem which we already proved.
Okay, thank you, sir.
Yeah. Any other doubt? Okay, so let us proceed. So now suppose that the dimension of n is positive. Okay, so let r equal to dimension of n is positive. Okay. Uh, yeah. So now we use the trick that is used very often to reduce problems about modules to problems about R mod P. R mod P is a special class of R modules. These are integral domains, much easier to handle than arbitrary modules. And this is made possible because of the Noetherian property of n. Okay, n is a Noetherian module. So it's a finitely generated module over a Noetherian local ring. And Noetherian modules can be filtered. Okay, there is a filtration of submodules n equal to n0 containing n1, containing n2, and ending at 0, such that when we take the quotient modules, they are isomorphic to R mod some prime ideals. Okay. N1 over N2 is isomorphic to R mod P1, and Nn minus Nn is isomorphic to R mod Pn minus 1 for some prime ideals P0, P1, Pn minus 1. Okay. And in the theory of associated primes, we also prove that the associated primes of the module are contained in this set of prime ideals. And this set of prime ideals is contained in support of the module. Okay. The containments can be very strict, but the minimal elements of these three sets are the same. Okay, the minimal elements of these sets are same. Okay, yeah. So since X behaves well on short exact sequences, if you have short exact sequences of modules, there will be long exact sequence of X. So to prove that these X are 0 or not, we could just look at these quotient modules. But then we have to make sure about the condition that I is less than depth of M minus dimension of M. So let us compare the dimension of N with the dimension of these quotient modules. Okay. So how does the two dimensions compare? So take dimension of Ni over Ni plus 1. Okay. This is equal to dimension of R over the annihilator of Ni over Ni plus 1. But annihilator of Ni over Ni plus 1 is equal to annihilator of R mod Pi. So this is just Pi. Okay. This is dimension of R mod Pi. Right? Now this Ni's are contained in Ni over Ni plus 1 is contained in N over Ni plus 1. Okay, so annihilator of N will be contained in the annihilator of all the quotient modules. Yeah, is that clear? So we know that the support of N contains all these PIs. Support of N contains all these PIs. So but support of N is the variety of annihilator of N. It contains all these prime ideals. Okay. So therefore, how do you compare the dimension of R mod Pi and dimension of N? Yeah, to calculate the dimension of the module N, I have to look at saturated chains which contain the annihilator and end with the maximal ideal. My ring is a local ring. So dimension of N is length of saturated chains, the supremum of lengths of saturated chains between annihilator of N and the maximal ideal. That's the dimension. But these annihilators, annihilator of N is contained in every Pi. and dimension of R mod pi will be supremum of lengths of chains between pi and R. So it is clear that the dimension of n is bigger equal to, so dimension of R mod pi is less equal to dimension of n for every I. Is this clear? Yeah.
Yes.
So if I prove the theorem for n equal to R mod p, I would have proved the theorem because the statement is for all finitely generated modules n. So in particular, it is true for R mod p. But this argument says that if I prove the theorem for R mod p, then I would have proved the theorem for arbitrary n. Yeah. Once you prove it, prove the vanishing of x ties on these quotient modules, you just look at short exact sequences which will arise from this chain. If this chain was just consisting of, say, 0 to n1 to n, then I will have n1 n and n mod n1. This exact sequence. Okay. So if I prove that I need to prove, understand x tie R and M. Okay. So if I know the vanishing of x tie n mod n1 M and x tie of n1, then by long exact sequence, this x tie of nm will also be 0. Yeah. So this is 0 if the same thing holds for n1 and n mod n1. Okay. But n1 is R mod p1 and n mod n1 is R mod p0. Yeah. So therefore, if I have a longer chain of submodules of n, I just apply induction on the length of the chain of the submodules, and the inductive step will start from here. And once I prove it for all the quotient modules, then this long exact sequence will give me that x tie of nm is also 0. Yeah. Is this argument clear that if I prove the theorem for n equal to R mod p, then the general theorem will be proved for all the modules, finite modules over n. Is this clear? This is very important reduction. Okay.
So could you please explain this once again?
Yeah. So if I prove the theorem for R mod p, n equal to R mod p, then I would have proved the theorem for ni or ni plus 1, right? Because all these modules, ni over ni plus 1, they are isomorphic to R mod pi for some prime ideals. And if x tie of ni over ni plus 1 m is 0, okay, for the given range, this is if and only if for all I, if and only if x tie of n m is 0 for all I in the given range. We just trap n into n between these quotient modules, right? Ni to ni plus 1 to ni, other way around, ni plus 1, then ni over ni plus 1. I know, so write down the long exact sequence of x, and by induction, I know this vanishing will be implied if because ni plus 1 itself is descending to 0. Okay. So if I know the vanishing of x tie on ni over ni plus 1, and so this x tie NIM vanishing can be deduced from the xi of Ni plus 1m. So this is a reply induction on I. Is this clear?
Yes, sir.
Yeah. So we just prove it for R mod P. So enough to prove that xi R mod P M is 0 for all I less than depth of M minus dimension of R mod P. And here now, dimension of R mod P is positive because I already proved it when depth of N is, dimension of N is 0. That is reduced to Ries's characterization of grade. Okay. So dimension of R mod P is positive. So R mod P is a local Noetherian domain. R mod P is local Noetherian domain. Okay. So therefore, I have a non-zero divisor. Okay, R mod P. Okay, this dimension is positive. Okay, this dimension is positive. So dimension is at least 1. Okay, and this is an integral domain. So all non-zero elements are non-zero divisors or R mod P. So I pick an element in X in M, not in P. Pick an element X which is not in P. Okay, then X is a non-zero divisor on R mod P. Okay, so I have this multiplication map by X. It is an injective map because X is a non-zero divisor on R mod P, and the co-kernel is R mod Px. Okay, but R mod P, dimension of R mod P is R. This is a local domain, and X is X is a non-zero divisor on this domain. So think of this as a module. Its annihilator is P, and X is a non-zero divisor on this module. So by dimension theorem, a dimension of R mod P comma X is exactly R minus 1. Is this fact clear to everyone? When I went mod a non-zero divisor, dimension reduces exactly by 1. This is very important to understand. Should I explain that?
Yes, sir.
Yeah. So Professor Patil has proved the 3 characterizations of dimension. Do you remember that? There were 3 characterizations of dimension. One in terms of the degree of the Hilbert polynomial, and then another was in terms of system of parameters. Yeah, and the original definition is through the dimension of the topological space, which is dimension the support of the module.
Yes, sir.
Yeah. So the last definition that he covered was this one. From that characterization, this dimension argument dimension count follows, because this dimension, first of all, from the dimension theorem itself, it follows that this dimension cannot reduce by more than 1. Okay, it cannot reduce by more than 1.
Okay.
Yeah, if I go mod a single element in a ring, in a local ring, in a maximal ideal, dimension cannot reduce by more than 1. So if Rm is local and X is in M, then dimension of R mod XR is bigger than or equal to dimension of R minus 1. And equality holds if X is a non-zero divisor. Yes. So let me recall. Suppose the dimension reduced by more than one. Suppose this dimension is this dimension is strictly less than dimension of R minus 1. So let us say this dimension is D. Okay. So therefore, there exists y1, yd belonging to M. Okay, belonging to M, so that when I go mod the ideal generated by y1, yd, this dimension is 0. Yeah, that is from the dimension theorem. That it is the smallest number of elements, so that when you go mod that, you get Artinian local ring. So this is equal to dimension of R mod x, y1, yd, and that is equal to 0. Again, by dimension theorem, it says that dimension of R is less equal to d plus 1. Okay.
Okay.
Yeah. So yeah, but that is a contradiction, right? Because this fact says that dimension of R mod xr plus 1, which is d plus 1, is strictly less than dimension of R. But this is the opposite. So we get a contradiction. So dimension, when I go mod a single element in the maximal ideal, dimension can only be one less or equal to the dimension of R. Okay. And x is called a parameter. If the dimension reduces exactly by 1. And did Professor Patil define system of parameters?
Yes, sir.
System of parameters in a local ring?
Yes, sir.
Yeah. So if dimension of a local ring is D, and x1, xd are in maximal ideal, then x1 up to xd is a system of parameters if the dimension of R mod x1, xi is dimension of R minus I for all I. Okay. Yeah. So,
Yes,
so
sir.
we had, yeah, somebody had a question. So I picked a non-zero divisor on R mod P and looked at the multiplication map. And this dimension is R, this dimension is R, and this dimension is R minus 1. Okay, this dimension is R minus 1. So we can apply induction hypothesis on R mod P comma X. Okay. Induction hypothesis on R mod P comma X because the dimension is reduced. Yeah. So this dimension is R minus 1. So by induction hypothesis, X I R mod P comma X M is 0 for all I less than depth of M minus dimension of R mod Px. This is R minus 1. So this is K minus R plus 1. So all these x's are 0. I, when I is less than K minus R plus 1, x I R mod P comma X M is 0 by induction hypothesis. So now we want to prove the theorem for R mod P. Okay. Now prove it for R mod P. Well, the trick is the long exact sequence. So you have R mod P to R mod P to R mod P comma X. On this, apply Hom R, okay, Hom R dash M. This is a contravariant functor. And it gives the long exact sequence of the X modules. Okay, so take the X module at ith level. And then the I plus first level. Okay. Yeah. Now this is the multiplication map that gives rise to the same multiplication map. Okay. This you have to go back to long exact sequence and check that the multiplication map gives rise to multiplication map at the X level. X are all linear functors. Okay. So now you see, by induction, I know that this module is 0 for all I plus 1 less than k minus r plus 1. Yeah, I just proved this by induction. That means I less than k minus r. This module is 0. Okay, so this is 0 in this range. If I is less than k minus r, I plus 1 is less than k minus r plus 1, and this module is 0, and this module is also 0, because I is less than I plus 1, and I plus 1 is less than k minus r plus 1. So that says that these two modules, this is an isomorphism. This multiplication map is an isomorphism. Is this fact clear to everyone? This is an isomorphism. Okay, so this X I R mod P M multiplication map X I R mod P M. This is an isomorphism for I less than k minus r. Okay, but all these X are finitely generated modules. Okay, these are all finitely generated modules, and X is an element of the maximal ideal. Yeah, so what can you do now? Can you predict the next step? Yeah? Nakayama. Yeah. So this is isomorphic to X times. This is equal. This is equal to X times X I R mod PM. So by Nakayama lemma, this X I is 0. For all I less than k minus r. And we are done. So you see, the trick was to reduce the main result. N was arbitrary finitely generated module. We didn't know anything more about that. But using that filtration, where the quotients are R mod P, it is enough to prove the theorem for R mod P. But R mod P, if dimension of R mod P is positive, we have access to a non-zero divisor, and that non-zero divisor enabled us to get a long exact sequence and use the induction. This trick is used all the time in this theory, that you want to prove a theorem for general modules. It is very often enough to prove it for R mod P and use the long exact sequence. Yeah, any questions? Yeah, before we proceed, any questions? Kanoy Kumar Das,
Yes, sir.
is this you have any questions?
No, sir.
Clear?
Yes, sir.
You are comfortable with the X modules?
Yeah. Yes, sir.
Okay. All right. Okay. So let us now. This has very important consequences. The Ishiba vanishing theorem has a lot of consequences. So let us derive an upper bound. So far we introduced the depth of the module. We don't know what is an upper bound of this. We know that it is a finite number, right? Because it was characterized in terms of vanishing of the X. Okay. So let us see a good upper bound on using the Ishiba theorem. Okay, corollary. Yeah. So we have a Noetherian local ring, Noetherian local, and M is finitely generated R module. Say finitely generated R module. Yeah. Then any M regular sequence is a system of parameters for M. Okay. So system of parameters for M was defined through dimension theorem. So system, if dimension of M is D, where M is a finitely generated R module over a local ring of dimension D, then system parameters consist of D elements. And these D elements are characterized by the fact that M mod x1 up to xd M has dimension 0. Okay. So how do you test whether something is system parameters? So this says that M regular sequence will be every M sequence is part of a system of parameters. Okay, not a system of parameters, but part of a system, because we may not have M regular sequence of good enough length. So any M regular sequence is part of a system of parameters. Part of a system of parameters for M. Okay, and the second, depth of M, that is length of maximal M regular sequence in the maximal ideal, is bounded above by dimension of R mod P, which is bounded above by dimension of M for all associated primes of M. Okay, so we get a upper bound. See, dimension of R mod P is bounded by dimension of M for associated primes. This is easy to prove. But depth of M is bounded above by dimension of R mod P for every. So in particular, dimension of M gives an upper bound on the depth of the module. Okay, so let us see that proof. So let us first prove the second, that the depth of M is less than equal to dimension of R mod P for every associated prime of M. Right? Yeah. So, yeah. So if P is an associated prime, We have to pick an associate prime and estimate the dimension of our, compare these two numbers. Yeah, P is an associated prime, means R mod P injects into M. Okay, by definition of associated prime, it injects into M. And therefore, the Hom of R mod P, M is non-zero. There is an injective map. Right? There is injective map is not zero map. So this Hom is not zero, but Hom is the X0 R mod PM. Okay, and remember the Ishiba vanishing theorem. Ishiba vanishing theorem said that X die R R mod P M equal to 0 for all I strictly less than depth of M minus dimension of R mod P. Yeah. So you see, if depth of M was bigger than dimension of R mod P, if depth of M is bigger, strictly bigger than dimension of R mod P, then what do you conclude? What do you conclude?
X0 will be 0.
Right. But X0 is not 0. Yeah, this will say that Hom R mod PM is 0. That is a contradiction. And therefore, depth is bounded. Depth of M is bounded above by dimension of R mod P, where P is an associated prime. Okay, where P is an associated. Is this clear? It says, quick argument using Ishiba vanishing theorem that the depth of M is less equal to dimension of R mod P, but P is an associated prime. Okay, and associated primes are contained in the support. This is variety of annihilator. So P contains annihilator of M. Yeah. So I have this diagram. So dimension of R mod P is less equal to dimension of M, because dimension of M is dimension of R mod annihilator of M. So therefore, we get that depth of M is a finite module over a local ring, is less equal to dimension of R mod P, and this is less than equal to dimension of M for all associated primes. Yeah. Is this clear?
Yes, sir.
Yes, sir.
Yeah. Manav, you have any doubts so far?
No, sir.
Yeah. Okay. So these proofs are very natural. Once you figure out on what to apply induction, etc., and which long exact sequence to use, things sort of go automatically on their own. Yeah. So now let's prove the second, the first fact, that if I have a M sequence, it is part of a system of parameters. Yeah. So that is the second fact. And it is enough to prove it for one element. That is, if X is M regular, then dimension of M mod Xm is dimension of M minus 1. Okay. That's the meaning of part of a system of parameters. Okay. So we have to estimate the dimension of M mod Xm. So we use the dimension theorem once again, that the when I go mod X, then the dimension cannot decrease by more than 1. Okay. So by dimension theorem, by dimension theorem of modules over local ring, dimension of M minus 1 is less equal to dimension of M mod Xm. Okay. Yeah. But dimension of a module is dimension of R mod its annihilator. Okay. And X and annihilator of M, they are certainly contained in the annihilator of M mod Xm. It could be bigger. Okay. Could be bigger. So it says that the dimension of R mod, the annihilator of M mod Xm, okay, that is less equal to dimension of R mod X and annihilator of M. Okay. Yeah. So this is dimension of R mod annihilator of M for X R mod annihilator of M. But X is M regular. Okay. X is M regular. So X is not in any associated prime. Of M. Yeah, it's not in any associated prime of M. Associated primes, they are part of the support. They contain annihilator of M, and this X is avoiding all the annihilator, all the prime ideals which contain in particular all minimal primes which contain the annihilator. This X is not in them. So when I go mod X, these minimal primes, they get lost. Yeah. So I have removed the minimal primes over the annihilator when I pass to X. So one layer of primes from all the prime chains, this is gone, and therefore this dimension is less equal to dimension of M minus 1. So this dimension is less equal to dimension of M minus 1. Because when I go mod this X times R mod annihilator of M, I have removed all the primes. Yeah. Which were X was not in any minimal prime of annihilator. So minimal primes of the annihilator are gone. And I'm estimating the saturated chains, length of saturated chain between R and the annihilator of M. So the lowest layer of primes, which are minimal over annihilator of M, they are removed when I go mod X. And so therefore, this dimension when I go mod X is at most dimension M minus 1. So in these all these inequalities are equalities now. And so when I go mod a M regular element, dimension reduces exactly by 1. Yeah. Is this clear? So dimension reduces by 1 and depth also reduces by 1. Okay. That is another fact to keep in mind. The depth of M mod Xm is depth of M minus 1. Okay. This is from the change of ring principle and the recess characterization, that if I take R mod I and M, and X is in I and M regular, then this X I is same as X I minus 1 R mod I M mod Xm. Okay. And then you use the vanishing property of the X to characterize the depth, and that says that depth of M mod Xm is depth of M mod. Or use that all maximal regular sequences in the maximal ideal, they have equal length. And if I pick, it doesn't matter where you start your regular sequence. So if I have gone mod X, then the length of maximal M regular sequence, M mod X, XM regular sequence has reduced by 1. So depth of M mod XM is depth of M minus 1. And if X is M regular, X is M regular, then dimension also reduces by 1. Okay, so keep these two facts in mind. Okay. Yeah. So another corollary. So let R be a Noethen ring. So now this is not necessarily local. R is a Noethen ring, and I a proper ideal of R. Then grade of I. Remember, grade of I is defined as grade of IR, maximal R regular sequence contained in the ideal. Okay, that is the grade of I. So so this says that this grade of I is at most the height of I. Height is defined already in dimension theory. Yeah, remember what is height? Height of an ideal. It's also called codimension sometime. So we are in Noethen ring, so it has finitely many minimal primes. Take these minimal primes containing I. Okay, so these are then the height of I is equal to the smallest. It is the min. No. Yeah, min of height P, where P contains I, and height P is the crude dimension of the local ring RP. So descending from P, look at saturated chains going all the way to some minimal primes in the ring, and look at the length of saturated chains descending from P, that is the height of P. And if I have an ideal, then look at all the minimal primes and compute their heights and take the min, that is the height of I. So it says that grade of I is bounded above by height of I. We approved general result that the grade of I on a module is less equal to dimension of the module. Remember? Yeah. Sorry. No, we proved the depth. Yeah, we proved the depth of a module over a local ring. Okay, depth of a module over a local ring was bounded above by dimension of the module. This is over local rings. So the height is derived from local invariants. Dimension of these local rings are P, where P is containing I. Okay, and yeah, and last time I also proved the following fact, that grade of I M is equal to infimum of depth of M localized at P, where P contains I. Okay, yeah, but depth of MP is less equal to dimension of MP. So this is less equal to infimum of dimension of MP, where P contains I. So that gives me that if I take it on grade, take now M equal to R. Okay, if you take M equal to R, then it will say that the grade of I is less equal to infimum of dimension of RP, where P contains I, and that is the height of I. So length of maximal R regular sequence in an ideal is bounded above by its height. So you can ask, when does equality hold? Okay, we will see that. We will see that R is Cohen-Macaulay. This is a theorem coming up later. I will define Cohen-Macaulay in a minute. If and only if grade of an ideal in this ring is equal to height of that ideal for all ideals. Okay. Cohen-Macaulay means so it is. So let me define now in general Cohen-Macaulay module and then Cohen-Macaulay ring. So we saw that depth of M is less equal to dimension of M. Okay. These are modules over local rings. M is finite module over local ring. Finite module over Noetherian local ring. So when equality holds, then M is called Cohen-Macaulay. Okay, that is first definition. Second, so this is for local rings. If R is not local, then M is called Cohen-Macaulay R module. If M localized at maximal ideal is Cohen-Macaulay R M module for all maximal ideals. So for local ring, I have this definition that depth of M should be dimension of M over a Noetherian local ring. Then M is called Cohen-Macaulay module over that local ring. If the ring is not local, then we localize at every maximal ideal and test whether M localized at maximal ideal is Cohen-Macaulay RM module for every maximal ideal. Then M is called Cohen-Macaulay R module. And if M equal to R, then R is called a Cohen-Macaulay ring. Yeah. So local ring is Noetherian local ring is Cohen-Macaulay if the maximal ideal has a regular sequence of length equal to dimension. We know that dimension is an upper bound on the length of regular sequence in the maximal ideal. Dimension is the upper bound. Yeah. So that is Noetherian local ring when it is Cohen-Macaulay. And if it is not local, then we call it a Cohen-Macaulay ring if when I localize at any maximal ideal, it is a Cohen-Macaulay ring. Yeah. So let us see one quick check on when a ring may not be Cohen-Macaulay. So if
Excuse me, sir.
yeah.
Sir, in proving grade of I less than equal to height, so the proof is fine. So can you go back to that page? Yes, so the page after this. Yes, sir. This.
No.
Oh, I'm sorry. Yeah, it was the right page. Yeah.
Yeah.
Yes, sir. Sir, in this, it doesn't change the proof, but still, like height being minimum, is there a reason it being minimum instead of infimum?
Minimum height.
So height of I being minimum of height of P.
No, infimum because the set may be infinite.
Right. So okay. So because in the beginning you wrote a minimum, so I thought, is there something more we know about the primes?
So if you restrict it, we know that the infimum will be obtained at some prime ideal, and that prime ideal has to be a minimal prime over I. Okay.
Right. Okay.
But there are only finitely many minimal primes.
Many. Okay.
So we can write min.
Okay, sir. Thank you.
If you restrict it to minimal primes over I, then we write it min. Otherwise, we write infimum.
Right. Okay.
Yeah.
Okay.
Any other doubt? Okay, so let us see that Cohen-Macaulay puts a restriction on the associated primes. Okay, so we saw that depth of M is less equal to dimension of R mod P, okay, and less equal to dimension of M for all associated primes of the module. And this ring R is local. Okay, this inequality we have proved. So if M is Cohen-Macaulay, then these are all equalities. Then depth of M equal to dimension of R mod P for every associated prime. For every associated prime of the module. This implies two things. Okay, there exists no embedded prime. Embedded associated prime. All associated primes are minimal, and not only that, they have equal dimension. Okay, all associated primes are minimal and they have equal dimension. So let us use this fact to produce a non-Cohen-Macaulay ring. Okay, so it says that there is no embedded associated prime. So if you look at, say, x square xy contained in polynomial ring over a field, then this has an embedded associated prime. This has following primary decomposition: x intersection x square y. This is a minimal primary decomposition. Of this ideal. So when I take the quotient by this ideal, if I go to R mod this ideal, this is my module, R mod I, associated primes of this R module, yeah, they are x and xy. So this is an embedded associated prime. This is a minimal associated prime, and this one is embedded associated prime.
Sir, it's x square y.
No, I'm writing associated primes, not the primary components.
Okay.
Xy is the associated prime. X square comma y is the primary component. M primary component. M is the maximal ideal xy. Yeah.
Yes, sir.
Okay. So therefore, so that says that R mod I is not a Cohen-Macaulay module. So let us understand. So that means the depth of R mod I is strictly less than dimension of R mod I. What is the dimension of R mod I?
One.
1, right?
Yes.
Yeah, this dimension is 1. Because you go mod the minimal prime, then you just get ky. So that dimension is 1. So depth is 0. So depth of R mod I should be 0. And why do you see that? How do you see that depth of R mod I is 0?
Because every element of the maximal ideal is 0 dimension.
Right. The maximal ideal is associated prime. When maximal ideal is associated prime of a module, then all elements in the maximal ideal are 0 divisor. So there is no M regular element. So this depth is 0. So that says that R mod I is not a Cohen-Macaulay module. That is one way in which a module can fail to be Cohen-Macaulay, that is by acquiring an embedded associated prime. But the other way is that all the associated primes should have equal dimension. That can fail. That can also fail. Yeah. So that can also fail. So I have exhausted my pages. Let me add a page. Yeah. Yeah. So let's look at R equal to K X Y Z over X intersection Y Z. And this is I. This is I. Okay, so I'm taking quotient of this power series in three variables by this ideal I, which is intersection of these two prime ideals. This is P and this is Q. Yeah. Okay. So we have 0 to R mod P intersection Q to R mod P, direct sum R mod Q to R mod P plus Q. P plus Q is what? P plus Q is the maximal ideal. So this is just K. Okay, this is just K. And I want to estimate depth of this. Depth of R mod P intersection Q. What is the depth of this module? What is depth of K?
0.
Yeah. K is just R mod M and M is associated. So depth of K is 0. Depth of K is 0. And what is R mod Q? R mod Q is Kx. R mod P is KYZ. Yeah. So what is the depth of R mod P? Yeah, tell me depth of R mod P. Do you think R mod P is Cohen-Macaulay?
R mod P, depth of R mod P is 2.
Right. And the dimension?
Dimension is also 2.
Right. So R mod P is Cohen-Macaulay. R mod Q is also Cohen-Macaulay, right?
Yes.
So, but they have unequal dimension, right? They have unequal dimension. So depth of R mod P is 2, depth of R mod Q is 1, and depth of K is 0. Okay, I want to estimate depth of R mod P intersection Q. What will you do? To estimate depth of a module, I need to know which of these X,
It's not vanishing.
which of these X are 0, right? Yeah. So just K is the residue field. K is the residue field of R, right? R mod M. So I can estimate the depth 0 to R mod P intersection Q to R mod P, direct sum R mod Q to K to 0. Yeah. So what is your guess about depth of R mod P intersection Q? Okay, so So we need to understand. Last time I proved the depth lemma, right? I proved the depth lemma, remember? Depth lemma. In that depth lemma.
So infimum of grade of I means grade of P, comma in
Yeah.
grade
So
of Q.
there's a special case of depth lemma that suppose this depth is 0, then depth of M is 1. Go back to the depth lemma or apply the X, long exact sequence of X, and you will see depth of this ring is 1. Depth of R mod P intersection Q is 1. But what is the dimension of R mod P intersection Q? Is X intersection YZ. Okay. So X is a minimal prime, and then you have XYZ. I have a maximal chain of length 2 here, so this dimension is 2. Or you apply the various fact about dimension. Dimension in exact sequence is the max of the 2 dimension. So this dimension R mod P was having dimension 2, and this has dimension 1. And dimension of the direct sum is max of the 2 dimensions. So this is 2-dimensional. This is 0-dimensional. Okay. And the dimension in exact sequence is the dimension of the middle module is max of the dimension of the 2 modules. So this module has dimension 0, and so therefore this is 2-dimensional. But the depth is 1. Okay. Depth is 1 and dimension is 2. So there is no embedded associate prime now. Yeah. There are 2 associate primes, P and Q, of R mod P intersection Q. Neither P is contained in Q nor Q is contained in P. Both P and Q are minimal, but they have unequal dimension. So it fails to be Cohen-Macaulay. So Cohen-Macaulay condition imposes this strong condition on the associate primes that all associate primes have equal dimension. So embedded primes are ruled out. So in particular, it says that if I look at the topological space, which is support of M, yeah, the support of M as a topological space is the finite union of its irreducible components, and these are the this is the union of irreducible components of P, where P is a minimal prime. P is a minimal prime. P is so in the Cohen-Macaulay module, P is an associated prime of M, and all the dimension of the irreducible components are equal, and they are equal to dimension of M. All irreducible components of support of M have equal dimension. So embedded components are ruled out, and irreducible components or unequal dimensions are ruled out. So Cohen-Macaulay condition is a numerical condition. It is just saying that there is a maximal M regular sequence of length equal to dimension, but it has this geometric consequence that irreducible components have equal dimension of support of M. Okay, any doubts so far? Okay, so let me prove a small proposition before we stop. So we have a Noetherian local ring. And M a non-zero. So in definition of Cohen-Macaulay module, I should have said it's a non-zero module. Okay, so M is a non-zero finite R module. Okay. Then for all associated primes of M, the dimension of M, I mean depth of yeah. So finite R module, which is Cohen-Macaulay. Yeah. I want to take a Cohen-Macaulay non-zero finite R module over Newtonian local ring. Then for all associated primes, the depth of M, which we know equal to dimension of M, is equal to dimension of R mod P. Second, I take a sequence. I take a sequence in the maximal ideal. Then this is M sequence. If and only if dimension of M mod x1n M is dimension of M minus N. Okay. So whether a sequence is M sequence or not can be tested by dimension computation. If I have a Cohen-Macaulay module, then in a Cohen-Macaulay module, if I have a sequence in the maximal ideal, I can test it whether it is an M sequence simply by computing the dimension of this quotient module. Okay. Third, I can calculate grade of an ideal. So this is the maximal M regular sequence contained in the ideal, and that can be also computed by a dimension calculation. That grade of IM is equal to dimension of M minus dimension of M mod IM. Okay. Yeah, so I proved part one already. Yeah, that follows from definition. And the second part also I proved by I calculated if X is a M sequence. If X is M regular, the dimension goes down by 1. Okay. If M is Cohen-Macaulay. So you just apply induction on N to prove part 2. Okay. Let me just prove part 3. Part 1 and 2 are more or less proved. Let me prove part 3. That the grade of IM is dimension of M minus dimension of M mod IM. So you apply induction on the grade. Now it's a well-defined number. So suppose G is equal to grade of IM. Apply induction on G. So suppose G is equal to 0. Then grade of IM is 0. That means I has no M regular element. So I is contained in the set of zero divisors. Set of zero divisors are union of associated primes. So by prime avoidance, I is contained in an associate prime. Okay, I is contained in an associate prime. So now to prove the formula, I need to prove that the dimension need to show that dimension of M equal to dimension of I mod M. I mean M mod IM. So I need to estimate dimension of M mod IM. So let us do that. Okay, let us do that. Dimension of what is dimension M mod IM if I is contained in an associated prime. Okay, this is an associated prime. Okay, but you see, dimension of M mod IM is dimension of the topological space, which is support of M mod IM. Okay, so let us calculate the support. Support of M mod IM is equal to, this is M tensor R mod I So this support is support of M intersection Vi. I is contained in P. So Vi contains Vp. Okay, this Vi contains Vp. So I have a subspace, support of M intersection Vp is a subspace. But P is an associated prime. Once P is an associated prime, it contains the annihilator. Support of M is variety of annihilator, intersection Vp. But P already contains the annihilator, so Vp is contained in the variety of the annihilator. Okay, so support of M intersection Vp is equal to Vp. Vp is variety of annihilator of R mod P, and that is the so therefore I have proved that support of M mod Im, okay, it contains variety of annihilator of R mod P, okay, and therefore dimension of R mod P is less equal to dimension of M mod Im. Yeah. Okay, for every associated prime. So what does it say? You see, remember the condition on M. M was Cohen-Macaulay. M was Cohen-Macaulay, and P is an associated prime. So dimension of R mod P is dimension of M. So dimension of M is less equal to dimension of M mod Im, but dimension of M mod Im is less equal to dimension of M anyway. So let's say that these are equal. So we are done in G equal to 0 case. Okay. If G is positive, then I has a M regular element. So when I go mod this element, then the grade reduces exactly by 1. And also the dimensions are reducing by 1. Dimension of M mod xm is dimension of M minus 1. Okay. So then, does it prove the formula? Yeah, by induction, G has reduced. G has reduced, and grade of Im has reduced by 1, and dimension of M mod xm has reduced by 1. But dimension of M mod Im remains the same because x is actually contained in I. X is contained in I. So dimension of M mod xm over dimension of I M mod xm is same as dimension of M mod Im because that doesn't change. M mod Im doesn't change when I go mod x. Okay, so by induction it is done.